Hey everyone, ever wonder how self-driving cars really learn to navigate the road? It's not just about sensors or code, it's about teaching machines to think like humans. Today, we're diving into the science behind the latest breakthroughs in autonomous driving, and trust me, it's wild. Let's start with the basics. How do these AI systems see and decide? Traditional self-driving tech relies on separate modules for sensing, planning, and acting, like a team of specialists working in silos. But here's the game changer. Researchers are now using vision-language-action, VLA models that combine seeing, understanding, and acting all in one. Think of it as giving a car a human-like brain, where it doesn't just detect a stop sign, but grasps its meaning and reacts appropriately. To understand how we got here, let's walk through the 4 phases of VLA4AD's evolution. Phase 1, pre-VLA explainers. Early systems were like smart but clueless assistants. They could process data and make decisions, but they couldn't explain why. For example, a car might brake suddenly, but it couldn't tell you, "I stopped because a pedestrian stepped into the crosswalk." These models were good at reacting but terrible at reasoning. Phase 2, modular VLA4AD. Next up, researchers split the job into specialized parts. Imagine a team of experts. One handles cameras, another deciphers language commands, and a third plans the car's movements. This worked most of the time. But if one part messed up, the whole system could fail. It was like a relay race, where a dropped baton meant a crash. Phase 3, end-to-end VLA4AD. Here's where things got exciting. Instead of separate teams, models like Emma and OpenDrive VLA started thinking all at once. They'd take a camera feed, a voice command like "turn right at the church," and instantly plan the safest route. It's like a driver who doesn't just follow directions, but anticipates the next turn. No more delays, no more errors, just smooth, real-time decision-making. Phase 4, reasoning-augmented VLA4AD, the final leap. Adding common sense. Systems like ORION and Auto VLA don't just follow rules, they reason about them. If a pedestrian waves, the car might think, "They're signaling to cross, so I should slow down." Or if a construction zone appears, it could adjust its path based on past experiences. It's like giving the car a mental notebook of traffic laws, weather patterns, and even human behavior. But here's the kicker, these models aren't perfect. They still need to process data fast. Every millisecond matters on the road. They also have to avoid hallucinations, like thinking a stop sign is a yield sign. Researchers are solving this by training models on massive datasets, like BDD-X and nuScenes, which include everything from sunny highways to chaotic city streets. Take Drivemoe, for example. This model uses a mixture of experts approach, like a team of AI specialists. One expert might focus on spotting pedestrians, while another predicts traffic patterns. By working together, they make smarter, safer decisions. It's like having a co-pilot who's always watching the road, the mirrors, and the weather forecast all at once. Meanwhile, VLA4AD tackles the challenge of multi-modal fusion, combining data from cameras, LiDAR, and GPS into a single, clear picture. It's like giving the car super senses, letting it see around corners or through fog with unprecedented clarity. But how do these models learn? They're trained on massive datasets. Think thousands of hours of real-world driving footage. Researchers teach them to recognize everything from lane markings to sudden obstacles. But it's not just about data, it's about efficiency. Papers like SparseAD use sparse query-centric designs, focusing only on the most critical information. It's like training a car to ignore distractions and zoom in on what matters, making systems faster and less resource-heavy. The payoff? Models like Drivemoe improve trajectory selection, ensuring cars choose the safest path through complex intersections. Others, like RagDriver, use large language models to generate human-like explanations for their decisions. Think of it as a co-pilot saying, "I'm slowing down because there's a cyclist on the left." But here's the catch. Even with all this progress, big hurdles remain. Can we make these systems respond faster than 30 times per second? Can we prove their decisions are safe? And how do we ensure they handle the weird, rare situations that pop up in real life? Plus, getting these models to work seamlessly in the real world, after being trained in simulations, requires solving distributional shift and edge case robustness. So what's next? The future of self-driving cars isn't just about speed or sensors, it's about understanding. VLA4AD models are bridging the gap between machines and humans, making roads safer and driving more intuitive. And as these systems keep learning, they'll get better at handling the unexpected, from sudden rainstorms to confused drivers. Thanks for watching. If you're curious about how AI learns, hit that subscribe button for more deep dives into the future of technology. And don't forget to like this video if you want to see more on the science behind the machines shaping our world. Until next time, stay curious.